It's 3:30, so we're gonna start. We have a few people here, and there are like more participants that are logged in online. Let me introduce you first, and then I'm gonna pass it to you, and you can start with your keynote. So, Dr. Kareem is a professor of engineering and the director of the NARHAS modeling laboratory at the University of Notre Dame. He is the elected president of the International Association for Wind Engineering. He has been awarded numerous honors and awards, including the Presidential Young Investigator Award from the White House Office of Science and Technology. And he's also an elected member of the US National Academy of Engineering. Dr. Kareem is also the co-principal investigator of the SimCenter, and this is very relevant to this user workshop. So after he's done with his presentation, we're going to open the floor. You can ask him questions on the material he presented, but also you asked earlier some questions about the functions of the SimCenter. He's the right person to probably answer some of these questions. The title of his presentation, as you can see, is Computational Modeling and Simulation of Wind Effects on Built Environment at NSF's NHERI SimCenter. Dr. Kareem.
Okay, thank you. Good afternoon. And thank you for this opportunity to speak to you about this topic, computational modeling and simulation of wind effects on built environment at NSF's NHERI SimCenter and its role in EFs, including the one at Florida International University. We all get introduced to wind engineering and somewhere in high school with the Tacoma Narrows Bridge. So I thought that today is the digital world. Everything is going to be digital very soon, if it is not already there. So I thought I'd show you a digital version of what's happening to Tacoma Narrows Bridge. And these three portraits are sort of still shots from that particular simulation. So that connects to what happened to Tacoma Narrows Bridge to what is happening on a computational platform. So the title is going to be, I'll give you some background, very quick review of NHERI SimCenter that might answer some of your questions. DesignSafe, I'm associated with DesignSafe. You couldn't be co-PI on two, so I'm a senior personnel on that one. Then I'll give you a guided tour of computational fluid dynamics. For some of you that may be redundant, but you can take a little nap during that time. And a little bit about some case studies we have done and virtual wind tunnel. And then I'd like to give some examples of what we have done in the past, cyber physical multi-platform experimentation. So everybody probably are familiar with some chart of this type. We want to tailor our structures, and we have these four options. And most reliable options are the one which are wind tunnel and computational method. And of course, for general design of structures, we use codes and standards. And to some of these, full-scale monitoring can help. So I think this is a slide I had before NHERI, but I think NHERI is sort of a similar thing. You know, we have connected nodes of different facilities, computational or experimental, and they are overlooked by a cyber infrastructure platform, which is a DesignSafe, and SimCenter contributes more towards to computational methods. So experiments versus simulation, you know, that's always a little competition there. You know, I would venture to say that I do sort of both, or a dabble in both. So I can say good or bad things about either one of them. So CFD gives an insight into the flow patterns that are difficult, expensive, or impossible to study using experimental techniques. So here I've drawn some comparison between the two. In experiments, the resolution in space and time depends on sensors, but in case of CFD, we can have a very high simulation in space and time. If experiments are limited to the type of problems, but practically there is no limit on the CFD side. We have scale effects and turbulence modeling issues in wind tunnel, and we have inflow conditions and how they match our computational scheme has also some issues which people have not explored yet. Error sources, I think one of the biggest source of error is the flow disturbed by the probes when we are doing experiments. And of course, there are errors in the sensors and the measurement system. Similarly, simulation is not deprived of these errors. We got modeling errors, that's the biggest one. The model we use, how we discretize, iterations we use and how we implement a particular scheme. Here's a very good saying by Einstein. A theory, in this case it could be CFD, is something nobody believes, and that's, you can talk to many people and they might have this view, except the persons who made it. An experiment is something everybody believes except the person who made it. So this is always a dilemma between the two modes of operations we have. Now let's look at CFD challenges and perception. Aeronautical people are very successful in doing what they do with simulations, but for structures we have some issues. We have people saying, oh, the results don't make sense, they are not correct. In aeronautics area, there's a long history of CFD applications and they have matured their development. We have a very short history in structural engineering. People, the users are well versed in fluid mechanics and numerical methods because they are fluid mechanics people. Here we have structures people who are trying to do fluid mechanics by just taking a wind engineering class, which only talks about ASCE 7. So I don't think you will have a very good background unless you do your self-study in order to understand the complexities associated with CFD. Users, they themselves develop codes in aerospace mostly. We rely on commercial codes which are very general, so their application may have some issue for a particular class of problems. They're very lucky in one hand that their flows are simpler. We are not that lucky. We have the most complex flows. On top of that, we have turbulence, which causes things more. So if people say, oh, we should move from experiments to CFD, computational methods, but I think before we get to that, we have to show people the robustness and accuracy of our results through validations with experiments, that this is indeed the way to go. Once again, I think just preaching for CFD is, in principle, I say, a most effective means of overcoming some of the challenges. And it can also combine advanced data analytics approach and has the promise to provide data with great details that are not possible in wind tunnels because of sensors limitation or their interference. But the major challenges we have is numerically capturing the complexity of massively separated flows. Structural engineers are faced with these massively separated flows around structures, which is compounded by multi-scale fluctuations in flow due to turbulence and their nonlinear interactions. DesignSafe and SimCenter are the two centers part of the NHERI which are trying to alleviate these issues or try to face this challenge and try to come up with a solution. So very quickly, before we go, the Raison did that draw for wind tunnels in digital world, because people are always worried what will happen to wind tunnels. I don't think the time that we can fold wind tunnels in digital world, they remain essential as the success of future CFD-based tools, because that will heavily rely on there for validations. Wind tunnels can also provide you a source for very large data sets, which can end up into meta modeling and machine learning. The juxtaposition of wind tunnels and CFD would lead to more synergies and eventual maturation of the computational tools so that they become daily design office tools. This may lead the way to the promising new world of digital design with literally unbounded opportunities. That brings us to the introduction to NHERI Center for Computational Modeling and Simulation of the Effects of Natural Hazards on the Built Environment. It is led by Berkeley, and Notre Dame, Stanford, and University of Washington are partner co-PIs, and there are several other senior personnel from many other schools. This is a big vision, transform the nation's ability to understand and mitigate adverse effects of natural hazards on the built environment through computational simulation. And it has various mission statements. I won't go through all the details. You can go to one of the websites and look into these. The tools have to be modern, extensible, scalable, secure, robust, harness machine learning and artificial intelligence, quantification of uncertainties, performance-oriented, and we have to help the decision makers and stakeholders at all levels regarding the performance of our structures. So what it is, the plan is that the computer, currently people rely on local desktop calculations. They're unable to scale to high performance computing, difficult to interact with with and move data from one application to another one. But if you move to cloud-based high-performance computing environment, provide plug-and-play capability to link multiple software applications together into workflows. Here is one example is that it will be application of applications framework. Here is the whole thing, and these are the parts which will fit in at various places. Here is, for example, the San Francisco city model experiencing an earthquake. So SimCenter would build workflows. Each component is a software application. It does something and has clearly defined interfaces. See, you have inputs, you got outputs. They use this scheme, Pegasus system for scientific workflow and management of the software. And the goal is to define the interfaces so existing and future applications of the user's choice can be used. Essentially, this will be a wrappers in the form of pre and post processors based on well-defined and documented APIs. This will create the correct input for an application given the workflow input and the correct output for the workflow given the output of the applications. So pre-processors and all these will connect. Existing applications can also connect. And using this approach, we will not need to modify any of the applications, and the developers can easily add new components into this framework. So what do we have? We have a front end. We will have front end GUI, which through Agave RESTful interface, which is quite complicated operation, but it connects through that to the DesignSafe. And there we have a host of different applications which will be soon coming, or some have already in operation. And that will have research applications will interact with through the DesignSafe. Everything will have to connect to DesignSafe, and your connection to us will be through the DesignSafe portal. For example, in case of wind, an event, because this is a multi-hazard, so we have all hazards here: earthquake, wind, and hydro. Hydro includes storm surge, flooding, and tsunami. And in case of wind, we have files of data, databases, CFD using LES and RANs, and we'll talk about those. Multi-fidelity model, multi-scale models, embedding WRF model into that. So we'll have OpenFOAM is the platform of choice. We will have a virtual wind tunnel for beginners to start off jumping into the game. And other codes will also be available. And of course, we'll use collaborators who have their codes, and they can be embedded into the system as well. DesignSafe is our platform through which we'll interface with the world, and it is hosted by University of Texas. Alan Rathje is the PI, and the rest of the people are involved with that. And in this particular case, I think many of you should open up an account. It is free, and start playing with this. It is a web portal. It has a data depot, Discovery Workspace, Reconnaissance Portal, Developers Portal, and Learning Center. So all these things are there. If you don't know anything about it, you open up an account and go into the Learning Center and start learning things and help centers. If you want to develop your own software, you're very welcome. You can use Developers Portal. And if not, if you want to use others, then you have to use Discovery Platform. And all those people who are measuring data, especially from your wind tunnel, that will be going into Data Depot, which probably you already are doing. So these are the main items. So Discovery Workplace is the one where most of the high performance computation will take place. And if you want to get started, here are the guidelines. You will click the button, and also user support is available. And I think they're very good if you email some question and that get responded very quickly. What is CFD tools, plans, and progress? As I said, everything is in open form. And it is, there are two ways we are allowing people to either directly connect to OpenFOAM on Stampede, one of the fastest computers in the US, or you can enter through DesignSafe portal, which I'll show you. And then we have various options of multi-fidelity modeling. Uncertainty quantification is a big thing, which I'll talk a little later in more detail. We also have we used to have a pilot virtual wind tunnel prior to NHERI time. Now it is being scaled up with more bells and whistles. CFD-based input to performance-based design, and I think learning hubs, which is, I think, an interesting concept. And especially those of you who are preparing career proposals, I think that learning hub might be a very useful thing to do. Here is just a general sketch to refresh our memories here. If you look at turbulence, it is a cascading large eddies going into smaller and then disappearing in viscosity. If I look at the plan view of a building, wind is coming from left to right. The green globs are the turbulence. And what I want to show is that we have three very dominant scales. Of course, turbulence is a quite broad-banding process, but we have these fluctuations here and these fluctuations, and they are their respective power spectral densities. So they have these three entities, they interact with each other. And, for example, a fine scale turbulence here would modify this thing as well as that. If you look at a 3D view of a building, and these globs are these eddies, which are coming, hugging your building, wrapping it around, twisting, tilting. So these are very complex nonlinear interactions, which finally result in buildings vibrating in the long wind direction across wind and torsion, or in case of low-rise buildings, we got tremendous pressures on the roofs of the buildings. The complexity, I said in the earlier that aerospace guys got lucky, that their problem is aerofoil. Nothing separates. So you can use models which are simpler to analyze some of these flows. As soon as we move from aerofoil to circular cross-section, we got, big region of disturbance here. Once we come into a structural engineering regime where we would have rectangular sections, you can see already that things are not only complex in the wake, but also in the shear layer areas. All these flows are governed by Navier-Stokes equations, which have nonlinearity, U here and a U there, and that's a bad news for us because there will be interactions, not at one scale, but at interscale also, which would create modeling becomes an issue in that case. Just to give you a little flavor here, what we are doing for researchers, we'll be looking at stationary models or forced oscillation models. Those guys who are interested in aeroelasticity, or we'll have a truly elastic model in which the model is allowed to rotate. Here is a typical vortex setting from a circular cylinder. Here are some examples which we have. These are the buildings and the flow without any disturbance in the approach flow. But if you add turbulence in the inflow, everything changes because of that. So these are just conceptual ways to realize what is happening in that case. Now come to what is CFD? CFD is not that I have fluent and I can read the manual and I can use it. You are lucky you might get the right answers, and you may not be lucky. And that's where the uncertainty regarding the reliability of results from CFD depends on. So you have to have a very good background in numerical methods, fluid mechanics, turbulence, and IT to some extent, so that you can manipulate your files and analyze the data. So the confluence of these areas is what CFD requires. And unfortunately, there are not that many people who have background in all these three areas enough to come up with results which are more reliable. So in order to look at the modeling approach, here is the flow, which has all large eddies, small eddies, and everything. And it is difficult to capture every detail because some of these small ones become so small that your cells or your grid becomes very, very large. And you'll see in the later slide how these things are. So best way is to do some coarse graining in which you only resolve computationally larger eddies, and then the smaller ones, you use some sort of a model. So it's a combination of resolving and modeling. So if I capture everything, that is a direct numerical simulation, which is almost very difficult for our applications. Large eddy simulation has a lot of hope for us. And RANS is Reynolds averaging, where you average the Navier-Stokes equations. And that is the simplest solution. It is very fast. But unfortunately, in areas where there's a sharp velocity gradients or a lot of separation, these methods have little difficulty in reproducing the results. Just here's an example. If you want to use direct numerical simulation, you need 5.6 quadrillion cells, which is not possible at this stage. So DNS is mostly a dream of some researchers doing some very fundamental studies in fluid mechanics. Large eddy simulation, as I said before, that here is the flow, you resolve it, the larger ones, and the smaller ones, you say, I'm going to use a model. And there are many models. These are just very few. And the accuracy of this depends very much on these models, because the big eddies, you have already resolved them computationally, so there's no issue. But the ones which are smaller, they are the ones which cause more difficulty. In case of Reynolds averaging, all fluctuations are averaged out. And by averaging operation, there is a new term which shows up, that's a Reynolds average coming from governing equations, and it's called Reynolds stress as well. And we have to take care of this through some sort of a model. So again, here are a few models, there are many more. There is another intermediate one, which is called URANS, unsteady RANS. In that, there is some low-level, low-frequency oscillations are included, which help us to get some idea about the fluctuations. So in summary, everything is put together here. The challenges I was telling you, we got very massively separated flows. If we come to this direction, wind is coming, separation here, possible reattachment, fluctuations there. And we have option to use LES or RANS. We need to, for high Reynolds numbers, we have to have the grid properly assigned. And then inflow conditions are equally important, because as you know in your wind tunnel studies, if you change the inflow conditions for the same body, you will have totally different aerodynamics of the body. So just again, here's a cartoon. Once again, these guys are very lucky at laminar flows, but you can use simple models. But as you go with a larger angle of attack, the flow starts separating. So similarly, we have to increase the fidelity of the model. The way they are showing, laminar flow, you can do closed form also. You have RANS, LES even better, and this is the best. So as the flow becomes more complex, you have to go to these more high fidelity models to get the results. In our world of circular cylinder, at low Reynolds number, everything is fine. But as the Reynolds numbers increase, we have to get into those high fidelity models because things become more complex. So streamlined body, going to bluff, very bluff, we have to increase the fidelity of our model. Otherwise, the results you're going to get are not going to be very reliable, and people will make these comments, oh, CFD. It's not CFD which is the problem. I think some of the problem has to be put on the users, because they are the ones who are making it believe that they are the right and everybody else is wrong. Here are the four of them. As you can see, RANS has sort of fixed frozen patterns here. URANS has some fluctuations. LES has more fluctuations because we can resolve them. And if you add turbulence, things get a little bit more. Just for relative comparison between the various methods which are going on. So for a CFD analyzer, again, I would not delve into the details because some of you might be getting bored already, because these are the things which you have been doing, the mesh generation, the space and time discretization, iterative solutions. And don't forget, this is the key part: verification, validation, and uncertainty quantification. People normally go and use Fluent with one grid, and they use another grid after that, and they say, oh, I've done grid convergence because the results did not change. But if they go one or two more steps, they might be surprised what will happen. So verification and validation of your simulation is very important. And of course, as we know in wind tunnels, we have many uncertain parameters which get into our problem, and that cause uncertainty, and that propagates through the system. And our solutions also have uncertainty, and that is the one where we can measure these error bars on our estimates, just like people do in wind tunnels. I think I've already spoken about this maturation, space, and time discretization. What are the tools available? Excuse me. As I said, Fluent, CFX, CD, star CD, and of course, open source code is open form and a very, very powerful code. And that because our program has to be all open source, so open form is the most obvious choice which we have used. So computational domain is again very important, just like in case of wind tunnel, in a small wind tunnel, not the big one like at Florida International University. If I put a very large model, I'm creating a blockage effect, and the effect of the walls is going to be penetrating. The same thing is we have to make sure that our domain is properly captured. We have unlimited space for the whole world, but if you have a plane flying by, it has a certain area which there's an influence on the flow. So the expected flow is like this, and this is a very good domain to capture because beyond that, the streamlines are becoming parallel now. But if somebody picks up this, say I'm going to use a smaller domain because I'll get results faster, and you miss these, and this is a very, very bad example because unfortunately, the Navier-Stokes equations are such that the solution at one point is very much dependent what happens somewhere else in the flow. So these things one has to keep in mind while developing the domain. Mesh generation, once again, we have all these boundary conditions, and we have to make sure that we have the right, we follow the right procedures. In case we are doing aeroelasticity, now the body moves, so the grid has to move. So these are some of the dynamic meshes we have developed. This is for circle cylinder, and this is for a rectangular case. Inflow conditions is very important. Just like in a wind tunnel, you have to develop, we use those spires and barriers at the inlet of the wind tunnel to generate proper type of boundary layers. The same thing has to be done in CFD. There are two major ways: a precursor method in which you have a surface roughness and you let flow develop and you rescale it and bring it back till it becomes a steady state. And then you connect that to your computational domain as inflow. Or there's another way is to use stochastic methods. You simulate stochastically, but the stochastics is not, they don't know fluid mechanics. So one has to make sure that the stochastically simulated processes have to take care of that. They have to be divergence free. Otherwise, you'll be mixing apples and oranges, and the results again would not make any meaning. So here is some work from Tetsuro Tamura's group, where they have been looking at a large complex of buildings and then zooming and looking at the details. And here are some of the cases where looking at the flow at different levels on the building. If another desirable issue is that we should have regional weather systems also coming and approaching your cluster of buildings. And in that case, WRF, Weather Research Forecasting Model, which is again an open source code. There are many people working in atmospheric science on those. Some people are combining WRF and LES through nesting. And some people are filling high frequency missing points in WRF. So there are various opportunities from the meteorological community, which we are going to be involving in bringing as a larger regional area flow simulation and nesting that into the local building. Those of you who are interested in fluid structure interaction, like VIV, buffeting, flutter, we have to have a transient solver, a structural dynamic solver, dynamic mesh, and all goes together and gives us our applications. And one is there is a fully coupled approach because now we have two systems. We got a solid mechanics and fluid mechanics coming and interacting at a, if they're fully coupled, which we don't normally do, that's more complicated and demanding. Mostly people use in our area is iterative coupling with sequential or partition. Just to give you a picture, you have a fluid dynamics domain, you got solid dynamics domain, and you got this interface which transfers information, has to do interpolation and other things, and grid modification, and goes back and next time start. And there has to be some iterations done in between. Once we have all these results, we have to do some post-processing. For example, you would like to visualize it, you like to calculate derived quantities, and I'll just give you some examples. And you have to do some statistical analysis, and of course, validation and verification are very important. Here's one example. For example, if you have a tall building sitting in your wind tunnel and we got these 600 pressure taps, and I have the same building in a CFD domain with the 1,000 pressure locations where I can have, they will start streaming out as your data comes out, and somebody has to manage that into a form so that it can be used wherever you're going to use. Here is one example we have in which we could combine the wind tunnel or CFD data into various floor loads. And if you give the mass, stiffness, mode shapes, it can do you more generalized loads, or you can couple it with open Cs and try to get these quantities. And many quantities of interest which are listed here, including the equivalent static loads, which could come out of that as an out. This is just one example. And also later on, this output from the CFD can be used to drive some experiments in the wind tunnel or outside the wind tunnel using some different devices, which I'm coming to in a little bit. So the hope is that we go from this is isolated building, and we go into a cluster of buildings or communities. Hopefully, we'll be able to do that, as currently AIJ, the Japanese Architecture Institute, has allowed to design buildings using CFD, and you'll know why in the next slide. But they have put one restriction that it has to be done under the supervision of an expert. So in old days, we used to do flow visualization with smoke. Now there's a digital version would be available soon, or it is in some places where you can visualize the digital flow after the simulation has been done using CFD. As I said, verification and validation is very important. Japanese have done a great job in this particular one. They're Kojima and Shimizu, two large construction company, they fund heavily CFD work, unlike in this part of the world. They have done a wind tunnel study of a cluster of buildings, and then they do a CFD model of the same, and they went to their supercomputer, very famous Japanese, the K computer, which they use 1 billion mesh points cells. And there are over 6,000 parallel cores, and they did this operation, as you can see, the results make pretty good sense. Comparison is almost on the 45-degree line. So this is the reason I think the AIJ has now come up with this provision that you could design your structures using CFD. But I think it's a very good addition they have made, that it has to be done under the supervision of an expert. Okay, now what we are doing at through combination of DesignSafe and SimCenter, we have those of you, best thing would be that if you are involved and you don't use OpenFOAM, just download the OpenFOAM manual and start reading some of the introduction, run a toy problem. And those of you who have, and you can open an account on Stampede, the computer, and here you are sitting as a preprocessor. These are the three basic system constant and poly mesh and the boundary conditions files, which you'll need to run the OpenFOAM code. Then as an expert user, you can go straight to the Stampede, pick one of these files, system, and through that you log in, batch mode, different nodes will be running your operation, and you will get your results. If you want to use the DesignSafe portal instead, which is a little bit more easier to use, in that particular case, again, these are the requirements or the needs of the OpenFOAM. You transfer them to DesignSafe's data depot, and that data depot is connected to the workspace where all you assign the files. Once the program is done, it will put back your results into the data depot. From there, you can do many things, including flow visualization. So I think it's a good exercise to start jump into it and see how it goes. At this time, these two tools, and the third one is also a very extensive database for aerodynamic loads on tall building models of all shapes, and a lot of shapes, and aspect ratios are also available for use. This used to be on our website, and we have expanded it and now moved it over to DesignSafe for more people to have access to it and use it. Now comes the question. We talked about RANds being sort of the low end of fidelity and DNS on being on the top one. In between is LES. LES has a lot of hope, as our good late Professor Fursiger, who was quite extensively involved with wind engineering community in early 90s in developing CFD. One of my students benefited a lot from him. And I think he used to say that if it turns out that LES can be done on very coarse grids, it will be one of the few times that nature has been kind to us with regard to turbulent flows. Because normally turbulent flows is an unsolved mystery. So people think that if we would be able to do that, that would be a great coup. One of the things which I have noted that, I started learning CFD in 1990, spent some time at University of Tokyo. And after that, coming back, we had one thesis on CFD, LES, flow around rectangular cylinders. But at that time, the computational resources were not available. So still, I see there is not that much of applications. So one has to see why. So I think one has to come up with solutions rather than just following the same approach. One of the things which I'm now trying, and some other people are also trying, is that you try to develop a multi-fidelity system in which you simulate things, say, in RANds, and you get the quality of LES through developing a multi-fidelity model between the two. And we have shown that in case of shape optimization that this particular approach works. But this will be only good for a certain class of problems. So one has to do, and many of you guys and others will start doing problems of your interest. We'll have a large collection of information, and then comes the data analytics guy, which will be able to sort out things. And down the road, people may not even have to do simulations because they will be sitting somewhere in the database, which can be connected through artificial intelligence, giving you some of the results which one needs. Other approach would be 2D simulations are very easy. You take a slice of a building, that's a lot easier to analyze than to have the whole building as we have here. I can do slice very quickly, but the whole building is a 3D structure, much larger domain. So what I suggest, and we did that several years ago in 2013, that we find the loading on a building at various levels, and then through some coherence model, we can estimate the overall integral loads on the structure. And here are some examples. We use Sears Tower, for which we have done a lot of measurements. So in that case, as you can see, the red one is our low dimensional model, which is derived from connecting or stitching together various level models. So we are not exactly the same, but it's providing a much reasonable solution. But at the same time, we spent a very little amount of time in computing the loads at each slice of the building. Here are some further comparisons of various quantities, and these are the base moments. And the more integral a quantity is, the better would be the match. The more local you will go, you will have some difficulty in matching some of the things. A virtual wind tunnel. Some of you may have heard about this one before. It is a combination of SketchUp, Facebook, and OpenFOAM. And in this particular one, we like to hold your hands and also give you some training because there is a large set of tutorials. And it is the engine behind that is OpenFOAM. So you are given instructions how to select your domain, what boundary conditions, what good turbulence model you have for this particular problem. So even we tested this particular wind tunnel, virtual wind tunnel, and asked people to find the drag coefficient of a slice of Empire State Building. We picked up 20 people from Notre Dame, 20 students from China, and 20 people from Amazon Turks, which those guys have no background in engineering, never heard of computational fluid dynamics. But after hearing that, those guys went through all this exercise, very large set of tutorials, post processing is available. And believe me, Those people who have never heard of CFD, non-engineers, came up with almost the same results as our students who are doing PhD in related fields. So crowdsourcing, if you teach people right, and tools like this will help expand the field of computational fluid dynamics, and it will become less of a fear for people to use. Now, jumping into this very quickly and briefly on uncertainty quantification, that's a major thing. As you know, many of you, aleatory and epistemic uncertainties of two kinds. This is natural one, we cannot avoid. This is because of lack of our knowledge. Through inflow condition, boundary conditions, initial conditions, model uncertainty, all these go into our numerical solution, and we have that an issue there. How do we quantify these things? There are some very sophisticated methods, which are called intrusive method, in which your formulation has to be recast in a stochastic version. But I don't think this method is ready for the type of flows we are dealing with. So we have to use something what we call as non-intrusive methods. Basically, the simplest of them is Monte Carlo simulation. In this case, the Monte Carlo simulation will be 1,000 times your CFD run, which again is very challenging. Or there are some ways, what I call, and some other people call, stochastic emulation. You use a reduced order model or surrogates. And in that case, you don't have to simulate 1,000 times. You simulate about 30 times, you get a surface, and then you can run your Monte Carlo simulation, and you won't have that much. There's a powerful tool, Dakota, again, open source, which has a host of schemes. And anybody interested, you should log in and download this particular source. And we are also developing this coupling between OpenFOAM and Dakota in the very near future. I think we should not forget some of the other techniques besides CFD, which are like model-based and data-driven simulations, time frequency models, Volterra modeling, detection analysis and simulation, translational models, surrogate models I just mentioned, and of course, machine learning is just taking over a lot of things. And it's nothing new for some of us have done these. For example, here is the hysteresis loop, which develops in aerodynamics. And you could model that very easily by artificial neural networks. And it's a very good way to handle and include the contribution of this fluid memory in there. As a designer, eventually you would like to see, where the digital world is going. I'm sitting here or somebody else is sitting here. I want to design a tall building. I want to do everything digitally. It's not like that. I have to come to University of Florida to go and do my wind tunnel study, then go to some other place for data for the wind turbines. The regional wind data. Then I have to talk to some experts in human comfort. Then what is the damping value? That is another big issue. So the hope is that we would have an integrated design concept through some engineering virtual organization, be DesignSafe, SimCenter, or some combination of them. So you are sitting here, you have access to modeling and simulation tools, which I just discussed on the last slide. You could have data-enabled design, that is measurements people have done in the wind tunnels before, which is now presently available on DesignSafe. And CFD, like I've described you, either you could go to Stampede or DesignSafe portal. Data, regional data is also available on internet now. You could, if you want to run experiment, like say at your place, you could also do by tele-experimentation like you guys are doing. So I don't have to come there, and you can do it, experiments collectively. There are damping databases now available, which help people to ascertain the value of damping needed for their design. And of course, we have a performance-based design tool, which does the human comfort in tall buildings for a certain level of probability of exceedance. You can pick out which is the right acceleration level. So in the last phase of this talk, I'm going to briefly go over cyber-physical infrastructure, which cross-platform validation is very important. As I said before, wind tunnels are going to be an integral part of your research proposals and others in validating what CFD does in wind tunnel experiments. We have to also, like your facility and the other University of Florida facility, hybrid hardware in the loop experiments have to become and I give you some examples. Conditional simulation based on measurements, and also driving actuation systems, driving a big hydraulic actuator which can put loads on a roofing sheeting or some other situation like that, using input from wind tunnels or from CFD. Just to give an example, many years ago, Lockheed Martin was interested in coming into natural hazards business, so they were looking at applying loads on structures by actuators which could mimic the earthquake loads or wind loads. So we have a discrete system, and we develop what we call a dynamic load system. And here is the example. In our grant, we did a 2 degree of freedom system. And once you apply, you are told that here is the time history of the load. And if you apply that onto the building is going to move, or the structure is going to move. And then you will disturb everything, and you would not have the same load applied on the structure. So this means dynamically you have to update your actuator so that it follows the load we have. So we did this little gadget here on which ball screw actuators were used in order to simulate that. It had quite complicated control systems and many other issues, but we eventually came up with a nonlinear controller, because in our case, we not only have to apply a desired loading here and there, but also we have to match their cross correlation. Because in wind, if we don't do that, we are not doing a very good job. Here are some examples of the correlated wind load, and the green is measured and the target was the blue one. So we faithfully replicated the load. This is called force control. Normally people do displacement control, which is relatively easier. A very difficult situation is when you're trying to control the force. We could also do with earthquake, because in earthquake, the load at each mass is the mass multiplied by the relative motion. So we could, same system can be used for actuating for wind or waves or for seismic loading. And I think that one of your visitors in the workshop, Professor Wu, has come up with this system, which is looking at the hybrid simulation of aerodynamics of a bridge, where you have the shape is in the wind tunnel, the skeleton is behind on a computer program, and they talk to each other at time steps. When the shape changes, it changes the load, and they iteratively they work together. And I think they have demonstrated not a 3D bridge model, but they have done a 2 degree of freedom system through their system to show that this particular approach using a virtual skeleton and a physical skin can help you to do the things together. Otherwise, you don't have to make a very sophisticated model, which we have to make otherwise. We have been doing a lot of things with sloshing dampers, and what happens is that the sloshing part of the fluid is very highly nonlinear, especially when you throw in screens in there. So typically, if you want to justify this one for a building, for example, this one in which this tank is currently located, people have a system that use a pendulum and which represents the building, and then you put the damper in there, and then you look at the performance. So what we had done in this particular case, what we call it hardware in the loop, or it's called, these days it's called hybrid simulation. Basically, you have this guy, the TSD, which is nonlinear on physical model, and this part is model on computer, where this part could also be excited by input directly from the wind tunnel in real time, or it could also be coming from some CFD type simulation. So they talk to each other at every time step. And this is an example. You have a force balance underneath, which provides the shear force, which the tank is inserting onto the building. And this works beautifully well in validating these things. Another thing is here, the nonlinear. I think we have to look into nonlinear things very soon. And here is a model I mentioned before, the Volterra model, that normally we work in linear models, and this is what we use, Duhamel's integral or impulse response function integration or convolution integral, we call it. But if things are nonlinear, we have to worry about somewhere in between. So if we use a Volterra series, which has a real first order term and the higher order terms, so these, you have to determine these kernels. Higher order kernels You can either do it by CFD, which we are doing currently here, with a single impulse or dual impulse. There are gadgets being developed. One of our former students in Italy has done that. And I think those gadgets can be done at your place in your internal also, where you could combine experiments of different nature to get some of the results to meet the needs of nonlinearity and unsteadiness. People also use in the wind tunnel some of the locations where they can measure velocity fluctuations. And then there are techniques conditioned on these measurements. You can simulate velocity fluctuations around those points. Some people have also done measurements with a rake of hot films here, and from those inputs, they are fed into a Navier-Stokes solver to look at the flow conditions as it passes by. Performance-based design, once again, I won't go into the details of every aspect, but somewhere we have to find loads on structures, and their effect would give us these fragility curves. So you can do it by wind tunnels, once again, database, or hopefully in the near future, everything could be done by CFD type analysis. I think we have all admired this Professor Davenport's chain, and codes and standards adopt this, and this is a very nice linear mode. But for you young researchers, I would say that things are changing now. And here we have come up with what we call generalized wind loading term. This is the same old one, linear, and we have to take care of non-stationarity because most of our winds are non-stationary. So everything goes from either time domain, frequency domain. Now we have to use time frequency domain together to capture these effects. And I think this is an area where a lot of research can be done utilizing wind tunnels and CFD. Turbulence structure interaction, this is a slide which has a lot of things on it. And as I talked about it, I have come up with an idea that turbulence is more like linear oscillators connected to each other through some nonlinear spring. Here is our structure, the body. Around the body is fluid structure interaction, which also is represented by these dash parts and masses. So their interaction between them and the role of damping and the turbulence can be interpreted very beautifully. And sometimes when we have more time, we can talk about this one. But I think CFD here is a long 1:5 aspect ratio prism. Wind is coming from this side. You can see so many areas which are defined by fluid mechanics people that you have to look for. And in CFD, we are able to identify them. Here's some example, or some of the coherent structures which are also, this is zoomed in here. So CFD provides a lot of detailed information for not for design purposes, but also for very extensive research. Same thing happens in case of circular cylinder. The role of turbulence becomes very, very important. Just to come back to this LES, which I mentioned, what happens is this is the spectra. Sorry for the quality of the slide. Here is the energy spectrum of the inflow. And what we do is we truncate it or we filter it at some scale. And we say we are going to resolve this part, but we are going to model this part. I think this, even at Florida International, has developed some partial turbulence simulation. And you see there are opposite trends here. They are defining the small scale turbulence, trying to model that in the wind tunnel, try to get proper results. In LES, we are using, not resolving it, but we are modeling it. And I think that's where one of the issues will come, whereas when we come to comparison of the results, where the large scale and the small scales have their distinct roles. Are we including them properly or not? I think another area which is good for cyber infrastructure is intelligent morphing, optimally marrying form and structure through sensing and controls. This is something we are currently working on through all these techniques, actuation, shape optimization, and using digital materials. For example, in aircraft, they are trying to use, as you can see, the plane can change the shape in flight. And I would encourage some of the youngest professors that contact your dean. Each year, the National Academy of Engineering has a global challenge in which they invite people to submit crazy ideas, and then they select some of them. And my student is presenting this idea in July in Washington, D.C. Hopefully she wins. So I think these are concepts. I'm sure that you have great ideas, and you need to try to make sure that they come to limelight and people know, because at forums like this, where there'll be many, many other young, smart people who would be interacting among each other and come up with better solutions to the problems which we cannot solve individually. So it's the last, I'm just very close to finishing. Here is a digital virtual learning hub. Some ideas for those who are writing career proposals. Well, I like to say fear out of CFD. We have to take it out, because all my career, I've always, oh my God, CFD is very tough. You cannot go with this. So we have to do that, something. And I think virtual wind tunnel would help it. And at the same time, I think we need to do crowdsourcing and learning from other people's contributions. You know, some of the Mosaic is a game which is developed, which through crowdsourcing, people are mapping brain cells, and the researcher is getting free help from the crowd to do some of those things. I think we need to promote solid understanding of fluid mechanics, appropriate for the simulation study, and the source of uncertainties and level of accuracy through an extensive online tutorials, webinars, seminars, blogs, and I call them digital learning hubs. We need to develop chat rooms, particularly geared towards wind engineering applications. Collaborations are very important in this case. So we, on the wings of next generation technologies, forever new frontiers, I think you should look for those and come up with ideas which you can use your wind tunnels, your CFD operations, try some of the problems which we have been solving. And in the closing, I would like to honor my inspirational luminaries. Some of you may not know: Von Karman, Professor Cermak, Professor Scanlon, Professor Davenport, Professor Shinazuka, who have provided me the role model to integrate knowledge from these various areas of research into innovative concepts couched in cyberspace. And with that, I thank you very much. And I'm sorry, I think I went a little bit more than I should have allowed time for questions, but I'm available. Thank you again. I think you guys are muted. Okay.
Very good. All right, thank you, Dr. Kareem. Can you hear me now?
Yes. Mm-hmm.
Right, yeah. So I think it's better if we ask the participants, the remote participants, to start with questions. I see that all of them are muted, but if anybody who's participating online has a question, please unmute your microphone and go ahead and ask the question. Let's see if anybody will.
Yeah, this is accurate.
See, only one person who unmuted his microphone. Jim, do you have a question? No. Maybe we can start with questions here. Anybody who has a question for Dr. Kareem?
I think that, because I asked the question for this session, I think Dr. Kareem may be, can you hear me?
A little louder, please.
Okay, I think that you are the right person to answer this question, because I'm curious, what's the relationship, or is there any overlap between the SimCenter and the CI Center? And can you comment?
Yeah. Yes, I think the official relationship is that anything we develop in SimCenter has to be handed over to computationally through right linkages to DesignSafe. and users will interact with those through the DesignSafe platform. You are not coming directly to us to say, hey, give me that one or give me that one. Does that help?
Yeah.
And the DesignSafe has two broader categories, or actually three. One is the hardware, one is data depot, another is simulation. The simulation, three of the people, including myself, team is dominated by the people who are also on the SimCenter. So that provides us very good way of avoiding duplications or anything which needs to be transferred quickly between the two groups.
Thank you. Hello, Dr. Kareem. To follow up on the previous question, we briefly discussed it in this workshop and we could not clarify it, so maybe you can give us some insight. So the particular question has to do with visualization and pre-processing and post-processing of, let's say, CFD models. Based on this chart that you showed, it looks like the user needs to submit the meshing, all the files that consist of, that make the model. So do you guys plan to provide some computational nodes that can handle the meshing, for example? Let's say OpenFOAM or Fluent are very demanding computationally when you mesh. You can wait a day for meshing just, if it's like million of elements. So, and most of the supercomputers that I have happened to use do not have visualization, because visualization is very hard to make work with Linux. So, and there are always compatibility issues. Yeah. Do you have any insight on that?
Yes, I think one thing is, I think it's a very good point you have made, because for some fiscal or technical reason, SimCenter started late and it could not have a users workshop like we did for the for the design, for the DesignSafe. So your question is a very valid question. Currently, the way it is that, as you saw from my structure, that you are responsible for developing your mesh. However, the good news is on the other end, on the tail end, where you want to post-process the data and use visualization, ParaView, or some other software, DesignSafe would be working on them. And I think we will, through SimCenter, also provide them some guidance, try what the user would be needing. But your point is very well taken, and I'm going to take it to our group back to SimCenter, that the grid generation is quite a chore, and people would need some help in that. Is that fair statement?
Yeah, that's very fair, and thanks for clarifying. I bet you will need some funding, because creating nodes for visualization is more expensive than having a node for just solving the problem. And we had to adjust our cluster at UNR and buy a head node that actually can do the visualization. So,
and also, I think for the success of SimCenter, we need to begin with a small users community who are experts and have experience like yourself or several others who are sitting in the workshop. And I would be getting in touch with you guys in very near future, try to have you try some of our things beforehand so that we can remove some of the issues before it becomes public. So I would be looking forward to your help because it's a community effort, and I think everybody has to pull together, whether you're part of the system in one fashion or another.
Thank you very much.
One question about the solver types. Seems like you were presenting mostly from a finite difference point of view with fluid. Is that correct?
It's a finite volume.
Finite volume.
Most of the OpenFOAM is finite volume, and I think majority of the CFD people have sort of gravitated in that direction. When I took the class many decades ago on CFD, it used to be finite difference only. And I think some people in mechanical engineering, they use finite element method. Some people use spectral method. Some people also use boundary element, depending on the type of the flow we are dealing with. But I think at the current focus is going to be on finite volume. And that's where other issues come when we are doing fluid structure interaction. you interact a structural dynamics of a structure with finite volume code. So interpolations have to be done in between. Would you like to have it some version of finite difference also?
No, actually, on the contrary, I was speaking to mechanical engineers, and they were talking finite elements. So
oh, I see. Yeah, all mechanical engineering. You know, last week there was engineering mechanics conference with very, very good contributions from some star researchers, and most of them were finite element.
Yes, thank you. I was attending that conference also.
Just one more question from my side. Is there currently any limitation on the number of cores that the users can take advantage of, and what is the process of assigning those? And the second part is if you have GPUs available that can speed up the analysis.
I'm pretty sure, I'm not aware about the GPUs and how they are assigned, but they do have. I mean, Texas Advanced Computing Center has a lot of, but right now they are making us available is through Stampede. The core, I think they'll, once you ask for too many cores, then the next question will come, have you scaled your system? How many, you know, after certain number of cores, unless it's parallelized in a proper way, you won't get much more efficiency. So I think few hundreds, I think, is easily possible. That's what I'm just saying based on our experience. But I think some people are using thousands also. But I think you'll have to develop some understanding with them, and they just want to make sure that their resources are not lost and are wasted. So I think if you develop a rapport with them and you're doing something and you are backing with an NSF grant, I think you will have very good success in seeking whatever you need. I think they've recently developed a policy, and I've not read it. It should be on their websites regarding these core allocation.
Thank you.
2 points, but firstly, I have to say that a wonderful talk. I enjoyed it. But my first point is about the notion of URANS model that you said can see some frequencies, low frequency phenomena can show comparing it with RANS. But I just want to say that by the virtue of time averaging Navier-Stokes, we kill the concept of time in RANS. No matter if you have the unsteady term or not, URANS or RANS it doesn't carry any meaning for time. So we should be careful about that.
I did, but I didn't mean that you are getting time. You get some, if you look at the spectral results from both, you will see some low frequency or energy in some low frequencies where you would see nothing in case of URANS, RANS only.
That's correct.
And
the other point that I had is regarding the body-fitted grid system that use ALE or body-fitted grid. OpenFOAM obviously uses. And regarding the type of problems that you work on, like moving structures and fluid-to-structure interaction, where the structure is moving. By moving your structure at every time step, it will dramatically reduce the quality of the mesh, and that has caused a lot of issues for CFD work that people do with ALE. Recently, there are other methods like immerse boundary method that people use, which is way more useful for these kind of fluid-to-structure interaction. And I think it's time for somebody to develop this immerse boundary method into OpenFOAM.
Yes, I think that's a good suggestion. As I said at EMI conference, there were many different schemes coming up for fluid structure interaction, depending on the level of how the structure was moving, or a bullet was going through a solid, how the grid was morphing. But I think with the scheme we have is we had a very good success in predicting post-flutter behavior of bridges. So, but I think your point is well taken that we should have variety and let people decide which particular method they would like to use. But you know, all these things, these are new methods, need some research element. Some or other, the overall understanding in case of NHERI projects is that you are not supposed to do research. See, and that's where the difficulty is, that even if you pick up something which is a well-established method and try to implement it for a general use, you need to do a lot of research before it becomes a usable product.
That's right. But there are open source codes available online that you can download, in which there are different methods, LES, DNS, and then the boundary method. Like the one model, for instance, is VFS, which is Virtual Flow Simulator, developed by Polyset Group. That's freely available online, can be easily used, like pretty much compatible with OpenFOAM.
Yeah, I think that we will be soon developing this directory of available online sources which you have. There's a very good group from Israel, I think Hazelman or something, his CFD group has a lot of interesting tutorials which are, these all would go into this digital learning hub. So people have these opportunities. If you are not surfing around looking for good CFD codes, others have done it, they can use it. But again, I think as a center, I'm not sure how diversified one can be, but there should be options for people to explore. That I agree with. And I think that another purpose of these is that you should be writing grants for proposals in ideas which you think that should be pursued. And I think that would be a very legitimate topic of funding.
Thank you.
Thanks.
So I just had a question actually that touched on most of the things that you said. So if you want to formally actually have a mechanism for collaborating with the SimCenter in the proposals that we're writing. So here, if I want to use the wall of the wind, for example, in my proposal, the facilities, as you said, the NHERI are not allowed to do research basically, but the facility will provide us with the expertise, how to use the wind tile, how to instrument it, how to conduct the test. The same thing, if I want to use the SimCenter, let's say to couple OpenSeas and OpenFOAM as you're discussing for like fluid structure interaction. How, as a PI, can I incorporate this into my proposal? Like, what are the lines of collaboration, basically, with the SimCenter?
The lines of cooperation would be that there would be some assistance provided to you if you have difficulty utilizing those tools. Other than that, it's a little different than these EFs, because EFs are experimental facilities, physical, something you can touch, and people can bring you and share the instrumentation, data acquisition. Computation is such a unique type of thing that somebody can only guide you. We cannot just give you in a plate and here it is and you take it. And it's a difficult thing which we are also trying to address. I think it's a very valid point. When some other people have raised it too, and we are raising it to NSF also to find a clearer picture on this.
So at least, is there a way that some of the gadgets that you develop to know like what's the progress, what's the timeline? So let's say again, I will just use the same example. If you are coupling OpenFOAM and OpenSeas, what's the timeline, for example, so that I can safely go and say in my proposal that I will use this gadget to study this application or understand this fundamental question, for example. Is there like a timeline that we can work like?
The timeline is, yeah, I think if I look at the proposal, there's OpenSeas or ETABS or any other interacting with OpenFOAM would be probably come next year.
Any other questions? All right. Let's thank Dr. Kareem again.
My apologies for not being there. Yeah. Anybody who has
Dr. Kareem, yeah. Go ahead.
Feel free to write me any question you have which you didn't get a chance to ask now regarding the work or connection to SimCenter or DesignSafe, at my last name, Kareem, at nd.edu.
All right. Thank you very much.
Bye.
Bye-bye.